My name is Rich Walters. I'm a research chemist with the FAA Fire Safety Branch. Today I'm going to talk about the preliminary results from the microscale combustion calorimeter interlaboratory study. This is work I'm doing with Rich Lyon and Natalia Safronova at the William J. Hughes Technical Center outside of Atlantic City, New Jersey. First, I'd like to talk about the microscale combustion calorimeter. It's a small scale test that measures material properties with just a couple milligrams of sample. One of the outputs that it measures is a fire growth capacity, which is a measure of the ignitability and burning rate of a material and presents the total fire hazard in a single value. Now, this MCC is a proposed method for an alternate means of compliance when a small change is made to a construction. Okay, here we have a cartoon that represents what goes on inside the MCC when we're running a test and how that relates to flaming combustion, along with the equations that we use to calculate the heat release rate based on the measurements that we make. When a sample burns, you have heat from the flame feeding into the material, thermally degrading it and producing the volatile fuel. Now, there's no oxygen at the sample surface because it cannot diffuse through the flame zone, so it's essentially anaerobic. As volatiles diffuse out, they mix with oxygen from the environment and react, forming complete and incomplete combustion products, along with heat. This heat feeds back into the sample, further degrading it and propagating the reaction. Now, we try to recreate what happens in the flame in the MCC. We thermally degrade a sample using a linear heating rate under nitrogen, which creates the volatiles, which are the fuel for the fire. We then add oxygen and completely combust it in a high temperature combustion furnace. We control the oxygen in and measure the oxygen out, and we can get a heat release rate using this equation on the right here, which is a collection of constants, our measured values, along with the correction for the carbon dioxide that's generated during the process. There are currently around 200 MCCs around the world. We developed an ASTM standard test method so that everyone runs the test the same way. I have an MCC curve for a thermoplastic shown here where we have heat release rate versus temperature. And we can extract a lot of information from this curve. First, at the onset of decomposition, we can get a value that correlates with the ignition temperature. Next, we can get a peak heat release rate value, which is a measure of how vigorous a material can burn in a fire. We can also get the temperature at which this peak happens, which is a measure of the thermal stability of the material. If we integrate and get the area under the curve, we can get a total heat release, which represents the fire load of a material. We weigh the residue, if any, at the end of the test and obtain a char yield. Here we have a sample that has a more complex heat release rate history. There's at least 4 peaks in this curve. So how do you represent this as a single value? Rich Lyon derived the value what we call the fire growth capacity. It's an integral method where you integrate the curve. This red curve here is the integral of this curve. And you look at the 5 and 95% temperatures and use that with this equation where we reference it to room temperature. And then we enter the total heat release from the sample, and that number gives us a value that correlates with larger scale flammability tests. Okay, so you got the fire growth capacity for a whole list of materials, and they rank pretty much as you expect. You have the commodity plastics or household plastics like polyethylene, polystyrene, things like that, linear hydrocarbon structures that burn pretty readily. Then you get into the engineering plastics like polyethylene terephthalate, your soda bottles, polycarbonate, things like that. The engineering plastics, they perform a little better because they have more double bonds and you start getting into cyclical structures. And as you increase those double bonds and cyclical structures, you get into the specialty plastics, which perform even better. And then you get into the heat resistant plastics, which is where the aircraft materials reside, the phenolic resins, PEEK and PEC, materials like that. Then you get into some halogenated and inorganic type of polymers, which are ultra fire resistant, but typically aren't used in aircraft because of how they're perceived. The MCC has worked out great for the fire research program in developing and identifying ultra-fire resistant materials for use in aircraft. But how can we apply this technology to the regulatory side? In 2015, aircraft manufacturers and suppliers asked the FAA for an alternate means of complying with the federal regulations. A similarity task group was formed to develop a method and criterion for comparing the flammability of materials using the MCC. Natalia Safronova worked on a similarity project where if a small change was made to a certified construction, such as a pigment change or a supplier of a certain resin was made, they could just test that component for similarity so the entire construction would not have to be recertified, which can be very costly. So we plan to use this FGC as the metric because it ranks the materials in the appropriate order for flammability and correlates with larger scale flaming combustion tests. So we looked at the statistics of all the FAA regulatory tests out there and found that at the 95% confidence level, values for a given material are plus or minus 30%. So we applied that 30% to the fire growth capacity, where if the difference of a certified construction material and a candidate material divided by the certified material is less than or equal to 30%, then they're considered to be similar, and this small change would not be detected in some of the other regulatory tests for certification. Moving forward, our sponsor Jeff Gardland is going to give a presentation at the tail meetings to see if he can get this alternate means of compliance approved. Also, I'm running an ASTM interlaboratory study to determine the repeatability and reproducibility of the fire growth capacity. And in this study, this is the second time we're doing a round robin for this, for the MCC. We're going to include an ultra-low heat release aircraft phenolic resin. Since the MCC is an ASTM standard, we're conducting our round robin according to the guidelines of ASTM E691, conducting an interlaboratory study to determine the precision of a method. And we're going to look at the repeatability, that's how well an MCC's data agrees with itself, and the reproducibility, how an MCC's data agrees with all the other MCCs in the study. Here's a list of values we're asking the participants to report on. First is the sample weight. We can get varying results if the sample is too large or too small, so we want to keep track of that. Next, we have the peak heat release rate, which is linked to the dynamics of the test and can give varying results if your heating rate is too fast or too slow. Next is the temperature of that peak. We want to make sure this value aligns with thermogravimetric data, which is what we consider to be the correct value. Next, we have the total heat release, and that's the integral value that does not depend on the dynamics of the test and should not vary by much if the flow and oxygen values are correct. After that, we have fire growth capacity, which is the new metric we are testing. We want to see what kind of variations we get for these more complex heat release rate histories. And finally, we have the char yield, which is the residue left at the end of the test. So far, I did a preliminary round where I sent out a polystyrene sample to the laboratories that were interested in participating to see what kind of data they provided and if they could provide that data in a timely manner. Now there's 4 manufacturers / licensees of the MCC. First is TTAC, they have the most units out there. And then there's FTT, and then Concept Equipment Limited. They licensed the technology, but I don't know if they have actually brought any MCCs to market yet. And there's me. I made about a dozen or so of these that are in circulation. So what I did was I took a polystyrene sample, sent it to over 20 labs. Several labs could not participate because their equipment was down and needed service, but I got data from 14 labs. For the most part, the data looked pretty good. Several labs need some minor adjustments, as I'll show you in the following slides. And in other labs, the equipment was fine, but the way they analyzed the data was wrong. Over the next couple slides, I'll show bar graphs where the bars show the individual lab values along with the dashed line, that is the average from all the labs, and dotted lines, which show the plus and minus 1 standard deviation. On the bottom, I have the outliers called out that are outside of 1 standard deviation, with the black bars being lower and the gray bars being higher. This first graph shows the peak heat release rate that had an average of 1,118 watts per gram with a standard deviation of 63 watts per gram or 5.6%. Ideally, we'd like this value to be less than 5%. 2 labs are considerably lower and 4 labs are a little bit higher. These values are related to the heating dynamics of the test and can be improved with a heating rate calibration. This next graph compares the total heat release measured, which produced an average of 40.6 kilojoules per gram and a standard deviation of 1.1 kilojoules per gram, or 2.8%, which is pretty good. There are 2 labs that were considerably lower than the rest. This is probably due to a bad flow meter or oxygen sensor calibration. Next, we have the fire growth capacity. This yielded an average of 868 joules per gram Kelvin with a standard deviation of 35 joules per gram Kelvin, or plus or minus 4.1%. Also not too bad, but could be better. This value had 2 clear outliers, one high and one low. These labs had values outside of 1 standard deviation for some of the other reported parameters, and fixing those issues could improve the FGC values. Next, we have the temperature of the peak. The average for this was 441 degrees Celsius, plus or minus 6 degrees, or 1.5%, which is pretty good, but the outliers are 10 to 15 degrees off, which is way too much. They will need to perform a temperature calibration in order to correct this. Overall, several labs need to make some minor adjustment to bring all of their data in line, but labs 3 and 14 were outside of 1 standard deviation for most of the reported values and will need further investigation to determine the extent of the problem and how to fix it. I don't show the char graph here because polystyrene gets completely volatilized and does not leave any residue after the test. So there aren't too many components to the MCC, so finding the sources of error isn't usually too hard. If there's a problem with the heat release rate, it could be a bad oxygen sensor, you could have a leak in the system, your sample size is too large or too small, you made a bad weight measurement or contaminated your sample, or the flow controllers or meter are out of calibration. If there's shifts in the temperature, it could be the thermal lag of the system isn't calibrated right, your data acquisition board is not calibrated, or the time shift for the system isn't right. So if there's a problem with the data, it can be attributed to one of these items on these lists. So I just finished collecting the data for round 1 of our interlaboratory study. So moving forward, I'm going to offer suggestions to the participants so they can make some adjustments to tune up their data. And then after that, we're going to enter into round 2 of the interlaboratory study with ASTM. I'm going to send out a set of 5 to 6 samples to all the labs, and you can see here's some data from the previous round robin, but this time we're going to include this aircraft phenolic, which is an ultra low heat release rate material, and you can see how that material scales with the other one. That's the green curve right here. It's a fraction of what the other materials are. And those results are going to be submitted directly to ASTM, so I'll have nothing to do with that. And then they're going to do all the statistics they need and update the precision and bias statement to get a good handle on the fire growth capacity number. And then when that's all done, I'm going to summarize those results and publish it as an FAA report. That report will be available on the FAA Fire Safety Branch website. Here's the address for that. Also listed are several reports that are currently available that cover the topics discussed in this presentation. First, we have a report on similarity that goes over the data and development of the alternate means of compliance we are investigating. We have one on the fire growth capacity, which goes through the derivation and significance of that value. We have one on the MCC development and its principle of operation. And we also have one on the last MCC interlaboratory study I did about 12 years ago. If you have any questions about any of the material I presented or any other work I'm doing, here's my contact information. Thank you for your attention.